It is tensor time! What's going on, smart people? Bringing you another episode of Tensor Calculus for Physics. I am super excited about today's video because today we are wrapping up the very basics of Tensor Calculus. After this, all of the key things in our checklist will be checked off before we can start doing things like taking derivatives of tensors and talking about covariant derivatives and whatnot. We have a lot to hit on today. It's a lot of smaller topics. The first thing, converting vectors and duals. We already know how to do half of this. We know how to go between vectors to the duals. We just don't know how to go back yet. Then we're going to talk about transformation rules for all tensors that have lower indices. We've been using the metric a lot. It's about time we prove that it is, in fact, a tensor. Then we're going to drop the whole upstairs, downstairs indices terminology. We're going to talk about contravariant and covariant and how they relate to ordinary vectors. More on what that means later. Now that we'll be working with tensors with upstairs, downstairs, and mixed indices, we need to define our tensor algebra. When can we add these things together? How do we contract indices? We'll visit that. And then finally, we know how tensors transform, but how do things like integration measures transform? Well, we know from multivariable calculus they transform via the Jacobian. How is this thing related to the metric? That's going to be the last topic of the video. In a future video, I should talk a bit about tensor densities and things like volume elements and how they transform. That'll probably be a short video in itself. So the next episode of this, we're going to move straight on to taking derivatives, but we will revisit this again in the future. Cool. Let's start with topic number 1. Converting vectors and duals. We already know how to do half of this. If we have the vector, we can find the dual by applying the metric. We went over this in the last video, so if we have some dual vector, we can find this dual vector by applying the metric tensor to the regular vector. Now, how do we go backwards? This is saying if I have this, I can find this by applying the metric, but what if I have the dual? How do I find the regular vector? Well, in order to do this, we have to define the inverse of the metric. So that obviously has to satisfy G inverse times G is equal to the identity. So we have a matrix, an inverse matrix times the matrix gives you the identity. And we're going to define the inverse metric with upstairs indices. So some G mu nu we can identify with G inverse. Okay, so component by component, what this is saying is that G mu, say lambda, G lambda nu should be equal to delta mu nu. So component by component, we're contracting, we're summing over lambda. So this is just going to give us something with mu and nu indices that should be either a 0 or a 1. It's 0 if mu and nu are not equal to each other. You get the idea. You know what the identity matrix is. Okay, so a quick example of something like this. We know that the metric for the matrix representation of the metric in, say, cylindrical coordinates is going to be 1, 0, 0, 0, rho squared, 0, 0, 0, 1. So in this case, the metric with upstairs indices, G mu nu, is going to be 1, 0, 0, 0, 1 over rho squared, 0, 0, 0, 1. And you can multiply these matrices together. Voice crack, oh my god, what am I, 13? And make sure that the matrix multiplication of this gives you the identity matrix. Okay? Okay, so we know how to convert the vector to the dual, and we know this relationship now. Let's apply the inverse metric to both sides of this equation. So we'll do some G lambda mu acting on A mu, and on the right hand side, still going to get that G lambda mu, G mu nu, A nu. And from this relationship, we know that this is just the Kronecker delta. So this is going to be, we're summing over mu, which is going to give us a lambda and a nu for our indices for the Kronecker delta. Lambda nu, A nu. And this Kronecker delta is just going to be changing the index of this A from a nu to a lambda. So this is equal to A lambda. In other words, we can collect everything, let the dust settle. G lambda nu, A nu is equal to A lambda. And there we have it. So now we can, if we're given the dual vector, we know how to apply the inverse of the metric to it to give us the regular vector. That's step 1. So maybe this is nothing too surprising to you. We wanted to find our a nu. We multiplied both sides by the inverse metric and we got it. Go figure. But what is pretty cool is the fact that we had to define our very first mixed tensor to do so, this Kronecker delta with upstairs and downstairs indices. So that's something that we haven't actually seen yet, which is new. So now we know that we can raise indices Josh Groban style by applying the inverse metric, lower using the regular metric. And this applies to tensors of different ranks. The only thing is you have to apply the metric once for each index that you want to either raise or lower. So say, for example, we want to end up with some tensor that has upstairs indices, mu nu, and we want to get this from a tensor that has only downstairs, let's say alpha beta. So we're going to have to apply the metric once for each index. So the first one is going to be, well, it's actually going to be the inverse metric, I'm sorry, because we want to raise the index. So we're going to have a g mu summing over the index that we're raising, which is going to be an alpha, and then g nu beta. So that's how we raise the index. And they don't all have to be raised at the same time. You can leave ones alone. For example, if we have some t alpha beta, we can just raise one of them. So if we apply g mu alpha, then that's just going to give us a t mu beta. So now we've constructed a mixed tensor from one that has strictly downstairs indices. The next thing that we want to do is we have these objects with downstairs indices. We know with the single index we're defining these dual vectors that should transform as dual vectors, and we got this prescription for how they transform from the gradient, right? We said that we have our d mu prime is equal to d nu dx nu over dx mu prime. So remember, since we have upstairs indices here, we're treating this as if it's downstairs, so we're summing over nu, we end up with something downstairs. So this is our prototype for how vectors with downstairs indices should transform. And we're going to extend this to apply to tensors of various rank with downstairs indices. So if we were to have some t prime, say mu nu, how do these things transform? How does the unprimed transform to the prime? Excuse me. Well, we'll have some alpha beta, and again, we're going to have indices upstairs for both of these so that we can properly sum over them using Einstein's summation. So we're going to have a dx alpha, and the denominator should be this mu prime, dx, and then x beta over dx prime nu. So this is very similar to what we did for the two upstairs indices tensor transformation rule. The only difference is since we need them to survive with downstairs indices, the displacements have to be in the denominator here. The displacements with respect to the prime coordinates have to be in the denominator here, I should say. And now that we understand this, we can apply this to mixed tensors as well. So really what we're doing is we're building a guidebook of saying if we have tensors of different ranks, you know, how do they transform? How do I treat them? How can I manipulate their indices? We're just doing a lot of bookkeeping and a lot of key things that we have to have down pat before we move on. So for example, one last example, if we have a mixed tensor, t prime, let's say mu nu, this is going to be equal to some other, let's do our alpha beta again. Now we need the alpha in this alpha coordinate to be converted into this prime mu, so the displacement needs to be in the numerator with the prime, so dx prime mu, and we need to sum over alpha, so the displacement in the unprimed should be in the denominator. I'm sorry if me explaining it is getting a little bit monotonous. It's just really important to understand where you sum over when you need to sum over. So we have, for the beta, this should be upstairs, dx prime nu. There we have it. So now we have the transformation rule for a second rank mixed tensor and a second rank tensor with downstairs indices. Cut off the alpha. Awesome. So now that we know how second rank tensors with downstairs indices transform, we have all the tools we need to prove that the metric tensor is itself a tensor. And the way that we're going to do that is we're going to consider the space-time interval, which we know should be an invariant quantity. So in a primed or an unprimed frame, they should be the same. So we have some ds squared is equal to ds prime squared. I'm going to end up dropping these parentheses because that'll be annoying. And we can expand both of these in terms of their metric times the coordinate differentials. So left-hand side, this is just some g mu nu dx mu. That's a mu. Don't let anyone ever tell you that's not a mu. Dx mu dx nu should be equal to, in some primed frame, g prime, say alpha beta, dx alpha prime, dx prime beta. Okay. The next thing that I want to do, I know how these should transform, these coordinate differentials. They should transform as vectors with upstairs indices. And I want to transform these in terms of the unprimed coordinates, which are going to be my mu and nu. So this is just the same thing as g prime alpha beta, and then I want to have a dx mu dx nu. How do I transform this into this frame? Well, I need to apply a dx prime alpha dx mu, and let me give myself just a little bit more space, dx prime beta dx nu dx mu dx nu. So now I'm just representing these in the unprimed frame because I know that this times these transformation coefficients should give me this. Okay? And now what I want to do is I want to take this equation and I want to subtract this one over. Okay? And then now that we both have these common factors of dx mu dx nu, I can factor them out. So what I'm really going to have is g mu nu minus some dx prime alpha dx mu dx prime beta dx nu g prime alpha beta times dx mu dx nu should be equal to 0. And this should hold for any displacements dx mu dx nu. So really, this is 0 if the argument on the inside is 0. In other words, g mu nu is equal to dx prime alpha dx nu dx prime beta dx nu g prime alpha beta, which is exactly the transformation rule for a second-rank tensor from a primed frame to an unprimed frame. Moving on from that, now we are ready to talk about covariant, contravariant vectors and how they relate to ordinary vectors, which I'll get into. For this section of the video, we are suspending the whole Einstein summation convention. So if you see repeated indices, we are not summing over them unless you see a summation sign. First things first, what the hell do I mean by ordinary vectors? When I say ordinary, what I mean is the coefficients of the unit basis vector in some orthogonal system in a Euclidean space. That's a mouthful. Orthogonal system, so I'm talking either Cartesian or cylindrical, spherical coordinates. Euclidean, meaning the elements of the metric tensor are all going to be positive. And since we're working in an orthogonal system, the off-diagonal components are going to be 0. We're going to be putting all this into writing if that was a little too much to just hear. So when I talk about ordinary, if I write something like a tilde, which is going to correspond to the ordinary vector, a tilde sub mu, right now this has nothing to do with covariant, contravariant vector, anything like that. All this means is I'm looking at the coefficient of the muth basis vector. So if I were to write my a tilde vector in, say, cylindrical coordinates, this would be a tilde is equal to a rho hat, plus a theta hat, plus a z, and these are all going to be tilted, z hat. So that's what these a sub mu tildes mean. It's just the coefficient attached to these basis vectors. The next thing that I want to do is I want to take a look at a line element, so our ds squared. So we know that our ds squared is equal to, now I'm going to explicitly write the summation over mu and nu, g mu nu dx mu dx nu. Going back to that mouthful that I said at the beginning, what do we know about our metric tensor in these kind of orthogonal Euclidean spaces? Well, we know that the metric should be diagonal, and we know that the elements of the metric should either be 0 or some positive value. So we can write g mu nu as the square of some real value indexed by mu times the Kronecker delta mu nu. And we have repeated indices, but we're not summing over them. So we can substitute this into this relationship here, summing over mu and nu. So only the diagonal terms, the ones for mu equal to nu, will survive because of this Kronecker delta. So this is just equal to h1 squared times dx1 squared plus h2 squared dx2 squared plus h3 squared dx3 squared. One important thing to note from last time we went over, or maybe it was the video before, I don't quite remember, but we know that the dx mu, these are coordinate differentials, and in general they don't have to have units of length, they don't have to correspond to a distance at all. But the h mu do. So this does correspond to a length, and this is because this is what the metric tensor does. It converts coordinate differentials into distances. So this is going to have units of length. Okay, how does all of this stuff relate to covariant, contravariant stuff? I'm going to go ahead and plop this stuff up here just to give myself some space. Contravariant vector components are related to the ordinary vector components in the following way. So we have A upstairs, so this is the contravariant vector component, is equal to A tilde mu divided by h mu. Now this seems a little bit arbitrary. Why are we picking it this way? It always comes back to the scalar product. We always want to preserve the form of the scalar product. So say that we wanted to take the dot product of two vectors. So we know that the dot product, we have to sum over g mu nu, we have to sum over mu and nu, mu and nu, and it's going to be g mu nu, a mu, b nu. This is our definition of the scalar product of two vectors with upstairs indices. Okay? And if we substitute in our definition of g mu nu and our, let's call it an ansatz, our guess of what this relation should be to preserve the scalar product, we get that this is equal to the sum over mu and nu. G mu nu is this factor here in terms of the h squared. So we get an h mu squared delta mu nu. A mu is going to follow this. So this is going to be a tilde mu over h mu times b tilde nu over h nu. This Kronecker delta is going to change the nu index to a mu, so really we just get a summation over mu of, so we got h mu squared, a tilde mu over h mu, b mu tilde over h mu. So this just changed the index on the b, and then these h mu's cancel, which just is going to give us, this cancels, and we sum over mu. This gives us our familiar a1 tilde b1 tilde plus a2 tilde b2 tilde. So we choose this kind of definition of the contravariant vector component to preserve the scalar product. Awesome, so we understand that we can relate this contravariant vector component with the ordinary vector component by this relation. Now moving on to covariant vectors. And this is where I actually kind of disagree with what the book does, because we're suspending the Einstein summation convention, and I think the book kind of sums over the wrong index, because when it defines the covariant vector component, it says that it is, the muth component is the sum over mu, somehow, of g mu nu a nu. And this doesn't really make sense to me because we're summing over the mu dependence. That wouldn't make sense to still have something with a mu index unless you renamed things at the end, but that's kind of a roundabout way of doing it. So instead, I just wanted to show you that this is what the book says, and I'm going to be doing something different. So I'm going to be summing over nu, because also otherwise we'd be able to pull the this component out because we wouldn't have been summing over it. So we're going to be summing over nu, okay? And this makes sense because this is just going to be lowering this to a mu. But let's go ahead and insert our definition of the metric and our contravariant vector component. So this is going to be the sum over nu of h mu squared delta mu nu times a tilde nu over h nu. Okay, and if we're summing over this, so this is saying this is equal to, h mu squared times delta mu 1 a tilde 1 over h1 plus delta mu 2 a2 tilde over h2 plus dot dot dot. So this is equal to our a mu. So we can pick a component of this. We can say something like, all right, well, what is the first one? A1. So A1 is going to be equal to, well, this delta term is going to go to 0 because we've got 1, 2, that component's 0. This is going to be the only term that survives. So this is going to be an A1 over H1 times H1 squared, which is just going to be H1 times A1 tilde. Okay, so component by component, we can identify that A mu is equal to H mu A tilde mu, where we're not summing over this index. So there we have our relationship between our covariant and our contravariant vector components and the ordinary vectors. There's a couple ways of thinking about what contravariant and covariant vector components are. There's a fantastic resource on YouTube uploaded by Eugene, I always forget the last name, who does nice little animations on what these kinds of things look like. So I'm going to leave a link in the description if you want to picture what exactly covariant and contravariant vectors are visually. But to give you the rundown real quick, I'm clearly not going to be animating anything, but for something like a contravariant vector, we can impose some coordinate system, let's say y and x, and here's our vector, and we're going to have our x basis vectors and our y basis vectors. And typically when we talk about vectors, the coefficients of those vectors are going to be how many of those basis vectors we needed. So if, say, one ends here, 2, 3, maybe 4. So let's say that this is the length of our basis vector. It's not really constant, but picture that these are a constant length. So this is saying if we have some vector v, then v is going to equal 4 of these basis vectors in the x direction, so 4 x hat plus, 1, 2, maybe 3 y hat. Now, if I were to change the definition of my basis vectors, more so by just changing the length of my basis vectors, like say that instead of this being the length of my basis vector, this was, so let's say that my basis vector is this long. Well, now it only takes 2 of them to give me my component of this vector in the x direction. So in this case, that went to a 2, and so on changes for y as well. So increasing the length of our basis vector decreased the component of our vector. So if your component of the vector changes in contrary to how your basis vector changes, we call that the component of a contravariant vector. And then the other way, I'm going to leave it, go check out Eugene's video if you want a better explanation for the dot product, for the covariant one, because it's in terms of the dot product of your vector with the basis vector, and in that way increasing the length of the basis vector also increases the component of the vector, so they increase with each other or decrease with each other, which are the components of the covariant vector. So that's a very quick, I kind of spoiled his video for you, but that's kind of how you can look at these contravariant covariant vectors. So maybe you can find that helpful. Okay, great. We know the relationship between the contravariant and the ordinary, and the covariant and the ordinary. Can we put this to use somehow? Yes, let's do a quick example. Let's remember the metric tensor for spherical coordinates. So previously, just a couple minutes ago, we established that g mu nu is just h mu squared times delta mu nu. the metric in spherical coordinates is just a 1, an r squared, and an r squared sine squared theta with 0 off diagonals. So that tells us that the h's are just going to be a 1, an r, and an r sine theta. So h, we'll call it hr, is equal to 1, h theta is equal to an r, and an h phi is equal to an r sine theta. So let's put this to use. Let's talk about the gradient. So normally when we talk about the ordinary gradient, it's the derivative of something, derivative of some scalar with respect to some position. So that's what this term is going to correspond to. And this a mu is just going to be some derivative with respect to some coordinate. And remember, the coordinates don't have to have units of length in general. So if we want to connect d mu, which is the derivative of something, it's the muth component of the gradient operator with respect to some coordinate, that's going to be equal to h mu times the gradient. And here I'm saying that this is the muth component of the gradient, which is the derivative with respect to some position. Okay? So that means that my gradient mu is equal to 1 over h mu d mu. Okay? And we know what these are. So that means that let's do this up here. Del r is just equal to dr. So that's just the derivative with respect to r. Del theta is going to be 1 over r, so 1 over r d theta, and d phi is going to equal 1 over r sine theta d over d phi. So summing these up and attaching them to their appropriate basis vectors, we get the gradient operator in spherical coordinates, just like that. As of right now, we're not ready to ask questions like, well, what about curl and divergence and Laplacians? We need to become more comfortable with taking derivatives of tensors first. For this, we're just taking derivatives of scalars, and we know that the gradient just takes a scalar and bumps it up to a vector. But if I take the gradient of, say, a tensor, does that up the rank of the tensor? Or if I take the derivative of a tensor, does that give me back the tensor of the same rank? These are things we don't know the answer to yet. That's going to start coming in the next video. So for now, we're just going to stick with this and come back to just tensor algebra. With tensor algebra, there's really 4 main algebraic operations you can do with tensors. And before we talk about them, one thing that I want to mention is the rank of a tensor. So if we have A contravariant indices, so upstairs indices, and B covariant indices, we say that the rank of the tensor is A plus B. So here we have 1 contravariant index and 1 covariant index, so 1 plus 1 is 2, it's a rank 2 tensor. Here we have 4 contravariant indices, it's a rank 4 tensor. And how it transforms just depends on whether it's mixed or if it's all contravariant, all covariant, which we now know how to handle. Okay, so the 4 main operations, first one's scalar multiplication. We can take a tensor of some type and some rank and multiply it by a scalar. It's going to spit out another tensor of the same rank and the same type, where all the elements of the tensor are just scaled by A, just multiplied by A. So that's the most basic one. We can also add tensors together. So long as they're the same type and rank, we can add them together. So if we have TAB, or alpha beta, S alpha beta, we can add these together to give A alpha beta. And one example of this is if we have some tensor, some second rank tensor, say, we can always split it up into a symmetric and an antisymmetric part that we're summing together. So we can always add an antisymmetric and a symmetric tensor together to give whatever our tensor actually is. Then we also have tensor contraction, and this is really like a generalization of the dot product. So with the dot product, we might have V, I, Wi, where we're summing over I. So we start out having 2 indices, and then we reduce the number of indices by 2, giving us a scalar. So for example here, we have a common index of gamma. That means that we're going to sum over gamma. So we reduce the total number of indices by 2, and we'll only have alpha and beta here. The next one is kind of like reverse of that, where we're increasing the rank. So here we're reducing the rank by 2, in a sense. Well, no, we're really just reducing the number of indices in our expression by 2. But we can also increase the rank. Here we have a rank 2 doubly contravariant tensor, and a rank 2 doubly contravariant tensor, and none of them have mutual indices, so we can form what's called a tensor product or the outer product, where we create a new tensor that has the rank of the sum of their indices. So here we have 2 and 2, so we have a rank 4 tensor here. Let's do a quick example of tensor contraction. It's probably one of the most common operations you'll do with tensors, so I think it'll be instructive to show that if we totally contract a tensor with itself, we get a scalar. So say I have some rank 2 tensor and I'm contracting its indices. I want to show that it is a scalar. Well, it's a scalar if its transformation coefficients are 1, right? If it's not actually changing when we do a change of basis. So if we take this as our primed frame, r prime mu mu, and I want to relate it to some unprimed frame, say rho sigma, well, so if I'm summing over this rho, that means the rho in the transformation coefficient has to be in the denominator. So that's a dx mu prime mu over dx rho, and then we have a dx here. We're summing over sigma dx prime mu, and this is just delta sigma rho r rho sigma. So this is just, we can change the indices of either of these, so this is just going to give us a rho, rho. So our transformation coefficients end up just being 1, so this is in fact a scalar. A good way, I think, to convince yourself that you can do this kind of differential swapping to give you the Kronecker delta is by just doing an example. So for example, if you do like polar coordinates, x equal to r cosine theta, y equal to r sine theta, then r is equal to root x squared plus y squared, and theta is equal to the tangent inverse of y over x. Then go ahead and pick examples of these sigmas and rhos. So if you let sigma equal x and rho equal y, then you're summing over mu, so you're summing over these indices, so that would be like saying dr over dy times d sigma d mu, so times dx over dr plus d theta over dy times dx over d theta. And see what that gives you. And then you could do it for other combinations of sigma and rho, and you'll see that if rho does not equal sigma, it'll give you 0, and if rho equals sigma, it'll give you 1. So that's a good little logic check to show if that made you a little bit uncomfortable. Just do an example, do an actual transformation. The last topic of the video is Jacobians. I know this video is getting long, I'm sorry, I didn't think it would be this long. But we've been spending a whole bunch of time, almost exclusively, on how different types of tensors transform, and now it's time to talk about something like how do integration measures transform. And for example, if we're integrating something, we can choose different coordinate systems to integrate, like a function with respect to. For example, if we want to do, say, an integral of some function of x and y, dx dy, we can integrate it this way, or we can just do a change of variables, in which case we're integrating maybe the function represented in r and theta times r dr d theta if we go to polar coordinates. And the way that we do this transformation is we take our new set of coordinates, say dx prime dy prime, is equal to the Jacobian times dx dy. And the Jacobian, J, is equal to the determinant of the matrix we build out of differentiating our new variable with respect to the old variable. So dx prime dx. So we're picking on polar coordinates. Let's do this as a quick example for polar coordinates to see if we get this at the end. So in polar coordinates, we know x is equal to r cosine theta and y is equal to r sine theta. So our Jacobian matrix would be the determinant of dx dr, dx d theta, dy dr, dy d theta. Okay? And so if these are our variables, this is just going to be equal to, I guess I'll write it down here, which is equal to dx dr is just going to give me a cosine theta. Dx d theta is going to give me a minus r sine theta. Dy dr is going to give me a sine theta. And then dy d theta is going to give me an r cosine theta. Okay, so taking the determinant of this, this gives us an r cosine squared minus r sine squared theta. So plus r sine squared theta, which is just equal to r, because cosine plus sine squared is equal to 1. Okay? So we do get the right Jacobian. We have our old variables times r corresponds to our new variables. So that worked. Now, we're taking our new coordinates with respect to the old ones. There's got to be a way of relating this Jacobian to the metric tensor. Now let's see how we can do that by looking at the transformation rule now that we know for the metric tensor. Okay? So I'm going to go ahead and plop this guy right up here. So J is equal to the determinant of dx prime over dx. And let's take a look at the transformation rule for the metric tensor. If I have some g prime mu nu, and I want to relate it to some old coordinate, let's say alpha beta, well that's going to be, you guys could probably do this in your head at this point, dx alpha, dx prime mu, dx beta, dx prime nu. Let's go ahead and take the determinant of both sides. So we do that, and the determinant of the matrix element of the metric, I'm just going to write as just the regular g prime in this bar. And this is going to be equal to this determinant, dx over dx prime, times dx over dx prime, times the determinant of g. Okay? And this is just the inverse of this, right? This is just 1 over the Jacobian. We're assuming the Jacobian isn't 0 here. So we have that this is equal to, and these are the same, so it's just going to be j to the minus 2 times this, determinant of the regular metric, in the unprimed frame. So that tells us that multiplying both sides by j squared, we get that, and then taking the square root and all that jazz, doing the actual algebra, j is equal to the square root of the determinant of g over the determinant of g prime. Now a lot of times we're going to be, our prime frame is going to be like our Cartesian coordinates. So in that case, our Cartesian metric is just going to be a diagonal of 1s. And if we have a diagonal matrix, the determinant is just the product of the diagonal elements. So the determinant here is oftentimes just going to be a 1. So we'll get that the Jacobian is just going to be the square root of the determinant of the metric. So that's the case where it gets kind of simple. In a future video, I'm sure I'll talk more about tensor densities and volume elements and things like that. It's necessary. But I'm going to call it for the video here. Hope you guys enjoyed the video. Let me know in the comment section if you made it this far, if you actually were able to watch the entire video. I know it was a long one. So let me know in the comment section if you enjoyed the video, and I will see you guys there.